Looks good.
All right, thank you. Yeah, great. So today I'm going to talk to you about the design and implementation of a drone calibration system for 21 centimeter experiments. So a lot of my PhD has focused on building a drone system, and I've had just a lot of fun over the past few years doing this. And I thought for this talk, I'd take you through a progression of some of that. So, I mean, in particular, the last few years, talking about some of the sort of starting instrument design and then preliminary flights and instrument upgrades resulting from those flights and all of this, culminating in our most recent trip in August to Green Bank, where we measured the Chime FRB outrigger prototype, which you see an image of on this title slide. So before I get started, I just want to quickly acknowledge the Yale drone group, who, this is work as a collaborative effort. So Laura Newberg is the PI. Belen Solowanchik was a postdoc at Yale for 3 years of it, and he's now at Brookhaven National Lab. I'm a graduate student along with Will Tyndall, who's a third year, and we collaborate on some of the analysis. Annie Polish is a postbac who was formerly a Yale undergrad, and then we've had two other undergrads, Miley Harris and Maya Walker, who have done a lot of work, and I'll shout out their contributions as we go. So I'm going to just start by assuming this audience is familiar with the great promise of active and upcoming 21 centimeter experiments. 21 centimeter spans so many interesting science cases, probes of cosmic dawn, epic of reionization, lots of FRB science recently from Chime, dark energy, name it. So, and I in particular actually focus on HIRAX. So when I talk about the drone system I'm building, it can be used in a lot of regimes, but actually I'm targeting it for HIRAX's 400 to 800 megahertz regime. So a lot of the design choices are made with that in mind. Anyway, so I've listed, so all of these experiments are, active and have lots of great things going on. I've listed GBT here, not because we calibrate it with a drone, but because it, of course, paved the way for other 21 centimeter experiments. And I just on this slide want to note for you quickly that all the arrays I've shown here have something in common, which is that they are big and they are stationary and they are not steerable. So for us to meet the promise of all these 21 centimeter experiments and get at these big science goals, we need to understand the beams of these experiments really well. So to 1 part in 10,000. But as I just showed you, these are stationary instruments. They're big and not steerable, so we can't calibrate them in the traditional way of pointing at a source and scanning. And instead, we ourselves create a movable source, and in this case, we fly one on a drone. No. Yeah, so drone calibration, in essence, just looks like flying our source on a drone over some section of the instrument we'd like to measure in a predetermined grid pattern, and making amplitude measurements for each polarization. And I've drawn just a little cartoon of what that can look like here. Actually, it's not really a cartoon. The traces are real flight data from a recent trip to Green Bank. But this is sort of the flight path a drone might take. So up into the far field, do a 2D scan, and then come back down. And there are a range of ongoing drone calibration experiments, Danny Jacobs at ASU and others. And yeah, there are a variety of ongoing efforts published and not yet published, and they differ in frequencies, drone platforms, source design, scan strategy, things like that. Let's see. Okay, so to perform this sort of calibration, the first most basic thing we need is a drone, a noise source to fly on that drone, and an antenna to transmit with. So the drone we've chosen for this is the DJI Matrice 600 Pro drone, along with the DJI RTK system. This has worked really well for us. It gives us about half-hour flight times in our far field, and the RTK we verified to give roughly centimeter positional accuracy. We start off with just, as a first configuration, a noise source, some attenuators and filters, right into our transmitter, and the transmitter we use is an Aronia Picolog 2300 antenna, and this is chosen because it's lightweight and broadband, and covers from, I think, 20 megahertz to 3 gigahertz, which is really helpful for capturing L-band dishes and other things like that. So this is the hardware we started out with. In October of 2019, our drone team visited Owens Valley Radio Observatory in Bishop, California, to measure one of the DSA 110 dishes. And I'll just pause here to thank Vikram, Medika, Greg, and other OVRO staff for making this really great trip. It was super, super valuable. So after we had assembled this first preliminary drone system, we needed a telescope to test at. South Africa, where HIRAX is based, is a little bit far, but thankfully we can adapt easily to L-band hardware. So we were able to fly over this L-band dish at DSA. So this was our very first beam measurement. Again, it's L-band, so we were looking at a frequency range of 1280 to 1530 megahertz, 4.65 meter dish. And our goal with this first visit was just to make a main beam flight, or capture just main beam slices in 2 cuts of this dish. And we had to do this with a manual flight. So I'll start by just explaining quickly what we flew and jump right into results. So the plot on the left shows a 2D flight path of the drone, like in a plane up in the far field. So the cross pattern that you see flies right over the center of the dish, and the points on the plot represent a drone position, where the color scale is the power measured at the dish. So you can see that, you know, the power peaks when the drone would be right overhead and then drops off as it finishes its pass. And I'll show plots like this often throughout this talk. I find this just a really convenient way to understand what we measured and just keep track of everything going on. So a big reason we flew this cross pattern was because we were flying manually with a controller, and it was a grid would not have been feasible in a manual flight. And we wanted to make sure that we were getting cuts directly through the center, or as close to the center of the beam as we could. So we'd sort of manually center, fly up, and at that point we, we'd just fly these 2 cuts. So just to show some results, we were really, really excited about these. Here's just a series of data as the drone passes through the main beam. You see, we clearly see Gaussians. The fits look great at a variety of frequencies. This was all really exciting to see. Additionally, we can look at, from these fits, the full width half max and how it changes with frequency. And we, which we plotted here, it's about the level that we'd expect. And something that was really interesting was that you see it has this sinusoidal pattern. It oscillates in frequency. And actually a similar pattern with the same period was observed, we learned later, in the DSA data from transit. So we were really excited and encouraged to see that we were able to measure this feature. Let's see. There were a few things we did not love about this measurement set. So one is just the frequency dependence of our measurements. So you'll see that the Gaussians that we measured are at a variety of amplitudes. And when you plot the noise source spectrum overhead with, you see as a function of frequency in the left plot, that it falls off very steeply. Which, you know, we would really like a much flatter spectrum so that we can reliably measure side lobes across our full band. And then, yeah, looking at this pattern and also our noise source spectrum normalized to peak power, they're very similar. This tells us we want a flatter noise source. So this was a really great trip, but we could do a lot better. So in addition to having a flatter noise source, also brighter so we can capture side lobes, we wanted to be able to measure the full 2D shape and not just the cross patterns, which, in addition to showing other interesting beam features, will give us a better chance at assessing the cross pole. So we can do a lot better than this. But our trip to OVRO overall was great. We made our first B map, and then, I mean, two other things that are not non-trivial that I didn't mention are we set our drone up for travel, which was a whole process, and then also used some on-site survey markers to verify this RTK GPS accuracy. So it was really instructive to make these measurements for the first time. But we came away understanding that we needed two main upgrades for our next series of flights. So it would be great to have an autopilot to get a full 2D map, and also, again, as I mentioned, a flatter, brighter noise source. And over the course of the next few months, we did implement these changes. So we found an autopilot that worked for our needs. Here's just an example of a flight path drawn in the autopilot. This is actually at Green Bank. But you can fly these gridded patterns reliably, which has been really great. And then an example of we obtained a noise source that was about 50 dB brighter, 45 dB brighter, and much, has sub dB variation across the band. So then after making these upgrades in March of 2020, our group went to Brookhaven National Lab in Long Island, New York to measure the BMX dish. And here our hosts were Andrzej Slozar, Justine Hout, and Paul O'Connor, as well as the BNL Cosmology group. And they were really, really helpful. So this was another incredibly useful set of measurements since we were able to deploy this upgraded system. So the BMX dish is a little bit more complicated than the dishes for DSA that we measured at OVRO. So similarly, this telescope is also L-band, so we're using some modified hardware. This telescope, we measured 4 different off-axis dishes, and our goal here was to measure both the main beams and side lobes and implement an autopilot flight. So the way that we do this, I've tried to illustrate here by outlining our flight path. So this is the just the drone path up in the far field in that plane in 2D. So we let's see, we do a series. This is how a typical set of flights would go for one polarization. So we do a set of north-south passes and a large grid at high power. So we expect in this flight we'll saturate the main beam, but we can get some side lobe features. And then we do the same thing in east and west to just fill out the plane. Then we attenuate our noise source further and make a smaller, denser grid to capture the main beam features and rotate our passes once again and do that. And the total coverage you should get from the full set of flights looks something like this. With the idea that in analysis afterwards, we would stitch together these high power and low power flights so we could have resolved main beam features and also side lobes. And here's an example of the beam information gathered for each flight and what it looks like overlaid, and all the color scales here are log. Yeah, let's see. And just as a quick illustration, again, a reminder that there was a lot of progress made between those October measurements and March. So this was really exciting for all of us. And with this new measurement scheme, we can get data that looks like this. So here we're looking at 2D maps in the same style, but for all 4 dishes, just at one frequency. And the origin of the coordinate system here is the telescope center. A few things to just note quickly. We do see side lobes, which was one of our main goals. So that was really exciting. We also see really interesting asymmetries and note that they rotate with polarization. And so it was a little bit challenging to compare this to what we expect, because with typical parabolic dish, we can look for airy pattern type features, but here with the off-axis dishes is a little bit more confusing. But I don't have the plot here, but have since looked at some simulation data, and it actually qualitatively tracks really well with these sort of asymmetric seeming side lobes. So that was great to see. And from this data, you can extract a whole host of useful information. So you can verify that looking at the left plot, the telescope looking at the telescope full width half max, or one of the dish full width half max is the function of frequency. You can see that its full width half max is centered at about 5 degrees in one dimension and 4.5 in the other, as expected from collaborator sims and computations. Let's see, and then you can just ignore these points on the right-hand side. There's a filter here, so they kind of look messy. So that was interesting to see. We were also, if you look at the right-hand plot, able to spot that certain dishes were a little bit mispointed. So you see overplotted here, the red points, these 4 are the dish location as determined from a flight where we hovered over the center of each dishes. That's shown in that faded blue in the back. And then the beam locations from fits are shown in orange. So here, 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 and here. And so this tells us that the telescope is mispointed. The dishes are shifted a little too inwards. And this is something that was very useful to tell BMX because they were able to correct this. And then the bottom plot here is just a visual of the main beam changing the frequency generated from using parameters from the 2D Gaussian fits. So you can see the beam size shrink overall and the beam condensing slightly about one axis. So this is great, but I'm hiding some of the hard stuff that went into making this analysis. So one of these hard things was that it appeared that the telescope and drone timestamps were slightly offset. So if you look here again at this same style of map where here the X and Y axes are both meters. This is just the drone flying over a dish centered at 0, 0. You would expect all of these, the centroids from each successive pass, these bright spots, to be in alignment, and you'd expect the overall beam to look rounded. So things are clearly out of alignment, and this is consistent, or this would occur if timestamps from the drone are out of sync with timestamps from the telescope. So one way you can check this and correct this is by applying timing correction between, well, what I did was between -1 and 1 seconds and 1/10 of a second increments, fit a 2D Gaussian at each iteration and plot the uncertainty as a function of timing offset. And if you look across all the parameters, the minimum is consistent through all of them, and that minimum should tell you the timing offset. So here it was about a 300 millisecond offset. And if you apply that offset, you see the centroids line up, the beam looks much more rounded. So this was an indication that there's something up with either our timestamps or the BMX timestamps that warrants further investigation. But at least we have a procedure for correcting timestamps if need be. So there was another feature that was a little bit frustrating. So we have this great autopilot. It can give us this 2D coverage, but its default was to stop the drone at the center of each pass. And so you can see there are like little arrows for each successive pass that terminate at the center, like along this axis. So at the center of each pass, the drone sees what it calls a waypoint and stops. And this we didn't realize in testing at Yale because it doesn't occur in smaller grids, only when you start to fly these really big ones. So the implications of this I've shown in these 2 plots down below. So for each, these are color-coded successive passes here, and then just plotted the drone's pitch angle as a function of distance in north, like along the north-south transit. And you see that at over 0, right over the dish where we'd want to be at the peak of our Gaussian, the drone does these wild swings where it pitches up to 20 degrees to brake and then quickly pitches the other way to reaccelerate and then resume motion. So this gave us some data where that was really noisy right overhead. And this was a challenge that we definitely wanted to correct for future flights. So there were, many takeaways. I mean, the main one is we accomplished our goals, and we were really excited to have seen side lobes have this more robust coverage, but there are certain non-idealities that we want to fix for the next flight. So we need a way to sort out the timestamps. We'd like to be able to pulse our source also so that we can get even clearer side lobes and have a better way of removing the sky background and drone RFI from our measurement. We also want to adjust the flight plan so that we're not stopping in the middle of the pass any longer. And also, I don't know if you caught that the date of this flight was March 2020. So we literally went to Brookhaven like the week before everything locked down. I mean, I drove back into my apartment and then like didn't leave for 6 months, so or more. So we also wanted a way after this to be able to make measurements more locally at Yale. Lockdown and sort of being grounded in New Haven without the opportunity to go do field work for a while did give us an opportunity to really work through all of these issues that we'd like to sort out. So I supervised a number of projects or collaborated on a number of projects with the undergrads and grad students, Annie Polish, Miley Harris, and Will Tyndall, who have been leading the way on Annie implementing and integrating a new GPS system into our drone setup with the idea that these timestamps are, should be GPS locked and very accurate and should, so give us a sense of help us sort out this timing issue. Miley Harris was working on characterizing different RF switches and also designing an RF switching board that we can use to pulse our source, and also upgraded our flight plans so that we no longer stop overhead. And then Will has been constructing this telescope at Yale. So we have built, or Will and our group have built this telescope at Yale that we have been testing some of our hardware on more recently. There are certain challenges. We're in the middle of New Haven, Connecticut. This is what our RFI situation is when you just walk outside. So we have identified this very tiny part of the band that we can use and just filter really aggressively around. So this is the telescope that Will has built to enable us to practice more locally. It's outfitted with a Vivaldi feed in the style of, I think, what they're planning for trying outriggers in the future. And this is just the Yale Observatory where we roll the telescope out to and fly. So we expected it to be really helpful to have this around. In April, it had finally been finished, April of 2021, finished, outfitted with a HiRX correlator so that we really knew we were taking the same style of data that we would see when we go out to the field to measure HiRX. But I don't know, plans don't always work out. So there were some bumps in the road. Even flying an automated drone is not so easy. In April, our drone flew away. So Yale, where we fly our drone, is over here, and then it passed all of, over here, and then it passed all of this civilization and passed all of this private property and somehow landed in a tree 2 miles away in the first public area, which was kind of a relief. So here's our drone on the right, stuck up in that tree. We were actually only able to find it because of this new GPS system that Annie had integrated into the drone. We were able to drive around New Haven, and when we got within range, ping that GPS and retrieve its coordinates. And then we kind of hiked into the woods a little bit and saw broken propellers on the ground and looked up, and there was our drone in the tree. So we discovered this at like 6:30 p.m. And then it rained all night and we didn't have time to get it down. But we found a professional tree climber who would do it for us. So we were able to safely retrieve the drone, repair it, and get it up and running again. So a lot of the work at the beginning of the summer and late spring was repairing the drone and also figuring out how to make sure that this never ever happens again. And so we determined there were two main things that went very wrong. So one of them was that this new GPS that we integrated we somehow didn't realize that it had a magnet in it, because it is for, apparently designed to, like, you just stick it on a self-driving car or something. So our new GPS had a magnet that was interfering with the drone's internal sensors and getting it really confused as to where it was. The other thing that went wrong was that the connectors between the noise source and the filtering were not properly tightened. So they weren't tightened down with an SMA wrench that day. They were just quickly finger tightened and put on the drone. And as a result, we've realized in later tests that considerable power can actually leak out of those connectors if not properly tightened and if shaking around. And so that power swamped the drone GPS. It got really blinded, didn't know where it was. I think I'm probably one of the few physicists who can say they literally watched their thesis experiment fly away, which was really wild. I think I didn't say this on the last slide, but it was flying its automated grid pattern and then just stopped and slowly drifted off. And there was nothing we could do about it. The autopilot overrides weren't working because all the communication frequencies were swamped. So thankfully everything was, thankfully the drone didn't land near people. It landed in a tree. Everything was okay. We were able to repair it and, diagnose the issues really carefully, sort of build it back up and test. And now we know better. Which brings me to once everything was repaired and once we were able to travel a little bit again, we finally had an opportunity to go to Green Bank, which we've been wanting to do for a while. So at the very end of August, our group went out and measured the Trime outrigger dishes there. And just huge thanks to Kevin in front of and all of you who helped us, get cars and get power and all of these things. It was a really great trip, and we really appreciate it. So we were measuring the Trime outrigger prototype at Green Bank. This was our first opportunity to measure a 400 to 800 megahertz dish, which was really, really exciting. We were actually able to measure 8 dishes, and these are F/D 0.38 dishes, which is just significant for us because for Hyrax, we expect to have much deeper, like F/D 0.25 dishes. So just like noting that there is this difference in design. And here we wanted to measure the main beam Gaussian and side lobes with an autopilot flight once again, but this time include a flashing noise source. And just want to emphasize that, as many of you know, we were there like a literal month ago. So the results I'm going to show are like super preliminary, but still it's been really fun to dig this data set. And we had a lot of fun while there. One of the things that we were able to do is get a tour of the Green Bank telescope, which was fascinating and just one of the coolest things. And that's also how I was able to get this picture. So this was taken from our GBT tour. And this just shows the dishes that we were measured. So the ones that were active are shown in red X's, and they're instrumented with a Hyrax feed, which was also really great because it was easy for us to grab simulations and compare. This black X right here is for there's this one dish is instrumented with a chime feed plus a different LNA. At the start of our week, we had our RTK base station, the GPS base station sitting over here. We take off the drone over here, and then you can kind of see our bench and stuff sitting over here. So we're trying to keep in the shade as much as possible. It was really hot. So that's sort of our setup. I mentioned we upgraded our noise source system for this trip. So this is what our board looks like now. We have our LiPo battery, voltage regulators so that it can send 12 volts to the noise source and 5 volts to power our switch. We still have our noise source, that same like 90 dB ENR flat noise source into just a standard mini circuits amp that passes like 415 to 785 megahertz or something, an attenuator chain into the switch, and then the switch switches between our noise source chain and a 50 ohm terminator, and then passes that to that same transmitter. And you'll notice this is all on like a mesh plate. We always fly a mesh plate behind our Beakalog because if we don't, the drone carbon fiber legs are like perfect reflectors at our frequency and the beam looks like nonsense. So, or it's not like smooth if we don't do that. So we've been doing that. I take a quick step back here and just talk a little bit about the beam ingredients to make a beam map. I know I've already shown several results, but because we upgraded our analysis to do some flashing, I just wanted to review. So there are two main ingredients, as you might guess, your drone data and your telescope data. I've already shown this drone data, but it looks something like this. The drone starts here, flies up to the far field, over to a corner, begins a grid. Here it's doing like 22 north-south passes, finishes up, comes down, lands. And here is the raw data in the correlator that corresponds to this. So these features right here are actually the Gaussians that happen as the drone transits, get closer and closer to the beam. This is where the drone would be flying directly through, and then further and further away. And this crazy spike is, I believe, where the drone is coming back down and getting really close to the dish. So here's just some example slices of what that looks like. If you zoom in, so in time, you have things that look like Gaussians, and the source is pulsing on and off. So this is what it kind of looks like. And then recently, Will has done a lot of work to tag the on and off points so that we can background subtract all our data. So this is sort of the telescope data. You take the raw data, you tag the on-off points, subtract it, then you interpolate the drone data timestamps to the telescope data timestamps, and you're ready to make your beam map. We had lots of challenges at Green Bank with the instrument, so I'll just start with number one, which is that there was no power at our site. So we were working with generators and had a lot of help from many of you with all of that. Still, here's Will initiating data taking in the dark with the flashlight. So the correlator is running out of the space bed. That is a little spooky without light. So that was a challenge. I made drove many laps to the Green Bank hut to recharge batteries and things like that. Another challenge is just that our noise source is bright. And so with the correlator set to its usual like configuration, we were just totally digitally saturating it. And you can see that here. So here's a waterfall plot on the left with frequency on the x-axis and time on the y. So these vertical stripes would be RFI features that are present for narrow frequencies, but for all times. These horizontal features would be like some broadband transient thing. So like a drone. So this is, the drone flies overhead. It's super bright at all frequencies for some amount of time, and then it's not overhead anymore. And if this is a saturation map of that data, and you see it just completely saturates when it's overhead. So we had to adjust the digital range on the correlator to make sure that we could reasonably make a measurement. So we just make the instrument much less sensitive, kind of made it stop being a telescope, but the beam should look the same. And this also, had the added bonus of now it's less sensitive to the sun. So we can just like not worry about only flying in the morning, things like that. So yeah, once we made the change, this is what drone flights look like. Now the drone, you can still see flights over the instrument with these stripes, but there's no saturation. So, and these challenges we sort of encountered one by one. I'm giving you them in chronological order over the first like 3.5 days of measurements. We also realized that analog saturation was a big problem. So once we were no longer digitally saturating, we were still seeing really weird features in our measurements. So here's a waterfall plot. You can see there's like a lot more RFI looking things than you'd expect at a radio quiet observatory. And there was this really, what we thought at the time was really weird, sort of intermittent, really bright flashing from like 670 to 700 that then reflects over 700 and it appears over here. So that's weird when we look at just that same, like how data, like time stream data, you'd expect, this is without flashing, smooth Gaussian looking features overhead, and instead you get all of this noise. So eventually determined that we have this RTK over here, base station. It's blasting a bunch of power to try to communicate with the drone at 900 and 930 megahertz. It has direct line of sight to a lot of our feeds. And yeah, it's just, and we are not filtering very sharply here before the RF over fiber chain. So we figure the RTK, and right, so the RTK transmits at 900 to 930. That would alias into our band at like 670 to 700, which is exactly what we're seeing. And it has these like little intermittent spikes that cover that range. So this is all RTK over here. So to remedy this, we moved the RTK location way back, far away from the dishes, also stuck it like where this building would block line of sight to the telescope. And things look a lot better now. So you see much, you don't see that feature anymore. Things look a lot smoother. Drones transiting here better. But this is flashing data. This still looks kind of weird. Like you'd expect one much better time resolution and a much smoother shape. So we still were not happy with this data and we were confused. Eventually realized that we were having some issues with writing the data. So because we didn't have power, we couldn't save to the computer internal SSD because it hadn't been backed up. So we had to save all our data directly to the hard drive that we brought, which it turns out just did not write data fast enough. So it was dropping a ton of packets and also just like smearing out timestamps, and things were getting really confused. Which you can see in this same sort of scatter plot right here where things look like a mess. So we were able to fix this by getting an SSD from Kevin. And now this looks as expected, and our beam looks round and like things aren't dropping out. So we overcome all these challenges and then finally are able to make some maps for the last half day of our visit. But from that, we were able to collect a really great data set. So I think I'm coming up, or I'm running a little bit low on time. So I'm gonna maybe just go through a subset of these things kind of quickly. But this is some preliminary results of our main beam data for 8 different dishes. And the coordinates are in meters relative, and where 0, 0 is the center of one of the dishes. And this is a map over, of the primary beam at just one frequency where the drone is flying these north-south grids. And just to highlight a few features, you can see the main beam really clearly. So you can see we'll get a good 2D fit out of it. You can also see some interesting first side lobe structure, and something that I thought was really fun was you can see these nulls are there are nulls in many of these that are out of alignment or sort of off axis, and in some of the dishes they slope downwards, like here, and in others they slope upwards. And actually we did not know the feed orientation with respect to the dishes, and we were warned initially it was very possible that like they were rotated differently for different dishes. So this may give us a very easy path forward for figuring out how the dishes are feeds are aligned with respect to one another. So looking at this structure, flip was really interesting. Yeah, and obviously further investigations are warranted. You can also look at the main beam results from one of the dishes and compare it with simulations and at a variety of frequencies. And I'll just give a few main takeaways here. So our main beam widths appear close. The side lobe structure appears in similar places. And I just think it's fun to sort of look over frequency at how at 700 and 750, you get this sort of smearing out of the beam that you can see reflected in our data as well. You can take just 1D cuts and compare those with SIMs as well. There's a lot of work to do to really understand the side lobe levels, but just preliminarily, here is what we have. And these are 1D cuts along Y, so just like the data from one of these slices directly through the beam. And you can see already that some of the side lobe locations are, or the beam widths look really good. They look really close. The side lobe locations are in a good spot. Or in, yeah, so that was really interesting to see. We can verify our fitting by plot from, we can perform a bunch of 2D fits and then just verify this fitting qualitatively for now by overplotting fit parameters against 1D cuts. So blue is fits from 2D and orange is data from 1D cuts, and ignoring the frequencies that we basically filter out anyway, things look pretty good. From you can also extract other interesting things from these Gaussian fits, such as centroid drift in frequency, which I was really keen to see this because the centroid, we've observed centroid drift in measurements of Hyrax feeds on other dishes before, and also I observed centroid drift in anechoic chamber measurements I made a few years ago. And they all dip in the 600 to 650 region fairly sharply. So this tells us that there's something going on with the feed, which will be good for Hyrax to know in their development. Can also look at full width half max as a function of frequency. And this looked really interesting as well. The levels are what we'd expect from simulations, which is great. Something also interesting to note is that whereas the simulation beams were somewhat elliptical, there was about a 1 degree difference in the full width half max between the two orthogonal cuts. The beams are much more round for our measurements. So that was interesting to see as well. So Marty, am I done? What time does this go to? Is it 1 or 1:15?
It's scheduled till 1 o'clock, but if you're coming close, you can go through a couple more slides.
Okay, yeah, I'll just show a few more. So, yep. So we can also look at our side lobe flights, and here I'll just point out a few features comparing simulations and data. I thought it just, again, being really qualitative. You see at 450 in the data this really fun-looking like petal pattern almost, which also is reflected in the simulations, and you wouldn't really be able to see that just from the 1D slices. At 650, I think there's this more cross type pattern that appears that is here, but a little bit rotated in our data. So that's interesting. And then you get that same smearing out of the beam at higher frequencies and also smaller side lobes. So that was all interesting. And you can, we flew these flights at high power. We expect saturated peaks. So here we just plot in 1D and again, look at just for sort of vague feature matching. And I'll skip polarization, or I'll just say a few quick things about polarization. Let's see. Or, you know, I'm running low on time. I'll also, we made while there on Friday, some drone transmitter beam measurements. So far we haven't taken into account removing effects of the beam, but we know we have to. So you probably all recognize this range. And we were thankful that GBO had a system that let us do this. And I'll just run through the takeaways of our measurements. Our beams are broad and smooth, which is what we want. There's some interesting features that we're trying to suss out whether they're from the antenna or range. And we took some measurements that will allow us to do that. And we'd love to follow these up with more measurements. So just to summarize, drone calibration is a promising new technique for making sensitive beam maps of stationary radio telescopes. I've built a robust drone calibration system that has now measured 3 different telescopes, and feedback from these flights has been really useful. And this recent visit to Green Bank especially provided a really rich data set that includes main beam, side loads, cross pole, drone RFI, a lot of things that we're just beginning to really dig into. So there's a lot of analysis forthcoming. But in the meantime, we're planning to come back on October 18th. We really want to get a good measurement of drone RFI in your EMI chamber and maybe follow up some far field range measurements and definitely fly again over the telescope and yeah, just get another set of flight data. So thanks so much. And with that, I'll take questions if we have any time.
Thank you, Emily. That was a really, really interesting talk. And I suspect now that folks have seen what you were up to, you'll have a lot more people down observing your next run when you come back in October. Does anyone have any questions for Emily?
Yes, Marty, I have one.
Go ahead.
You mentioned this RTK signal at 900 megahertz. Is that a required signal to support the drone flight, or is it something you can just turn off and let the drone run a preloaded pattern and then land again? And then you wouldn't have to worry about that interference.
Yeah, so it interacts with the drone in real time. So the RTK is necessary for this centimeter positional accuracy that we want. But I think we're starting to think that looking at how we handled the RTK at Green Bank could give us a path forward for using it at other telescope sites. Perhaps we could sort of shield its line of sight to telescopes with some sort of fencing thing, but maintain RTK lock with the drone when in the air. So, but yeah, it's unfortunately it is a requirement to have it running the whole time.
Christina?
Hi, Emily. Thanks for a really interesting talk. I was wondering, could you comment on possible applications with something like a synthetic aperture radar that might let you maybe take measurements of steerable telescopes like the VLA? Is that something that you guys are looking into?
Not at the moment. Yeah, I'm sorry, I don't think I can comment on that right now.
I guess maybe sort of the question behind the question would be, is there like an application where this type of like holography would do a better job than traditional methods used on arrays like the VLA or the NG VLA, for instance?
That is a good question. Yeah, I don't know off the top of my head. I think the motivation, at least behind this system, is definitely to enable, where holography would look like just getting one cut through the beam for these stationary telescopes, building up the full map. But I'm not sure how it would compare to calibration for an actual steerable telescope.
Okay, thanks.
Ron?
Yeah, thanks. Very good talk. Thanks. I'm also thinking about other applications. So one of the questions I've got is two questions actually. How high can you fly? Because to be in the far field goes as the dish diameter squared, right? So in order, so you're flying at 250 meters. If you want to do the same thing for the GBT, that would be 50 kilometers that you'd have to be flying. And the other thing is, and it's also wavelength dependent, right? The smaller the wavelength, the higher you have to fly. So how high can you fly? That's question number one. And the other aspect is the accuracy with which you're measuring positions of the drone, because that also determines things like whether you can use it for holography. So we thought about this for the GBT using some flying object as a transmitter for holography, but we would need accuracies of the order of millimeters in the position of the flying object. So so those are my two questions: how high and how distance accuracy.
Sure. So we're not flying at 50 kilometers. Yeah, I think the height we'll be able to fly is more going to be limited by what the FAA will allow us to do than how high the drone can actually fly. So one of the students I talked about on my group, Will Tyndall, is focused on using the drone to make a near field map and then understanding how that transforms into a telescope far field. Because, for a telescope like CHIME, for instance, we also can't reach the far field, but we'd really like to calibrate. So yeah, I think our thinking there is that you make a near field measurement and understand really well how to transform it. For positional accuracy, I don't know that it's not on the, so I have, okay, so you can, here's a measurement of just the drone. It's sitting stationary on the ground for like 20 minutes, the equivalent of a typical flight time. And we're just looking at how position jitters during that time. And so it does jitter within this like centimeter box, but for the most part, it's really, concentrated. The sigma of that is like a few millimeters. So yeah, so that's sort of the accuracy that we're getting.
Thanks.
Brian put a note in the chat about, I guess they tried measuring 140 foot with a helicopter, so that's kind of interesting.
Oh, wow.
Krishna, you had a question?
Yeah. Are you going to do phase measurements with the drone of the antenna?
So let me see. Let me think about this for a sec. We have not been doing phase measurements quite yet. Sorry, I asked this question the other day, so I have notes on this somewhere. Yeah, well, in this setup, we can't measure phase, but I know Kevin and my PI Laura are working on like proposals where they want to add additional hardware so that phase measurements are in principle possible. You could put a reference antenna somewhere, and but we do not measure phase in our current setup.
I think you would need them to do like near field to far field transformations, if I understand that correctly. But yeah, thanks anyway.
All right, any other questions? Well, if not, thanks again, Emily. That was a really interesting talk. We're looking forward to having you come back in October, and
Yeah,
and hopefully you'll come back and give us an update after you've done that next round of measurements.
absolutely. Yeah, really looking forward to it. Thank you so much.
All righty. Oh, a question popped in here at the end from Stephen. Do you have a second for another question, Emily?
Yep.
That was a hand clap, not a hand.
Oh, I'm
raise.
sorry. Okay.
Well,
Thanks,
I
that was
can
a
add
great
one.
talk.
Thank you.
Yeah, that was a really great talk. I have one more question if you have a minute. What
Yeah.
is setting you the dynamic range of your results?
So the this is done like in the correlator, and I was less involved in this piece, but my understanding is, are you asking like how we adjusted the dynamic range so that we weren't just saturating the telescope, or?
Yeah, I saw when you adjusted things so it wasn't saturated, but then it looked like your dynamic range was something like 30 dB, and I was just wondering if that was the correlator or something not related to the drone.
Yeah, that's a good question. I'm not sure.
And fundamentally, there'll be an integration time signal to noise. That might just be that.
Yeah, we are. I mean, we are integrating for less time, much less time than this telescope typically would, because we don't want to like, we would be there for years if we had to, wait 5 seconds at each little point. So yeah, I could certainly be part of it. But yeah, I feel like I'm not sure.
Right, thanks.
I guess, well, some of this is also just how we chose to set like attenuations on our like high powered flights, for instance, too, because I think we were measuring, maybe we measure the side lobes at some appropriate level, but then just like saturate the main beam like crazy, so you can't fully see that range anyway.
All right. Well, thanks again, Emily.
Yeah, thanks so much.
Good luck.
All right, bye.